Hello, everyone. So my name is Laurent Bernaille. I work at Datadog in the infrastructure team there. And I'm mostly on the team responsible for Kubernetes cluster. And just to give you an idea, sorry, of course, somehow I can't. Okay. So just to give you an idea, for those of you who don't know Datadog, we're a SaaS monitoring company. And we run at a pretty large scale, so you have a few figures on the screen. But things that are relevant to what I'm going to talk about today is we run the infrastructure we manage is tens of thousands of hosts, and we run tens of Kubernetes clusters from very different sizes, between 50 nodes to more than 2,000. And I'd say half of them are between 1,000 and 2,000 nodes. Another important point is we are multi-cloud, so we run on multiple cloud providers. And we grow very fast, which means the infrastructure has to follow. So very quickly, the main reason we chose Kubernetes are these ones, which are very specific to us. The first one, that's probably the most important one, is dogfooding. So because we provide monitoring tools to customers, we want our monitoring tools to be good. And 2 years ago, we noticed that a lot of our customers were migrating to containers, and we figured that the best way to provide interesting monitoring tools was to actually do it ourselves. And so that's why we decided to migrate to Kubernetes. And also, more normal reasons, we were using Chef to manage our servers, both on the operating system side and to deploy applications. And of course, you can imagine that when you have tens of thousands of servers, it starts to be a bit tricky. And then we were starting to migrate to multi-cloud, so add a second cloud provider, and we figured that having a single API would be a lot easier. And finally, the Kubernetes community was very dynamic, and it still is, and it was a very interesting point for us. So why is this talk called The Very Hard Way? So it's kind of a joke, because Kelsey Hightower has this amazing tutorial that's called Kubernetes the Hard Way, and it's a very good introduction at Kubernetes to learn how to start and create a cluster. So if you are new to Kubernetes, I highly encourage you to look at it. But it turns out Kubernetes the hard way is only to get started. It was actually much harder. And this talk is actually about the fine print. So if you look at a Kubernetes 101 story, a tutorial, a blog post, or Jerome's talk from yesterday, you're going to have a lot of disclaimers at the end in fine print, which, for instance, well, of course, this is a single master. You'll need to have several ones to be HA. Oh, and yes, well, there are certificates. You'll need to manage them and rotate them. And the final one also, well, by the way, networking is kind of complicated. If you want to do it in production, you'll have to look into CNI and Ingress controllers, so pretty complex topics. So here is what we're going to talk about today. It's what happens after Kubernetes 101 when you want to go to production. We're going to cover 3 main topics because we only have a limited amount of time. The first one is how to build a resilient and scalable control plane, then how to secure it, and finally, how to do efficient networking. So let's start with building a resilient and scalable control plane. So this is a Kubernetes 101 control plane. Usually what you build, you end up having a master where you run etcd, an API server, scheduler, controller, and you have your kubelet or your kubelets and kubectl connect to this API server. So that's fine, but of course, this isn't resilient. So the next normal approach would be to create multiple masters, and then you have something that's much more resilient, and you put a load balancer in front of it. So this works, and many people actually use this in production, but this is not perfect. The first reason is for etcd nodes, you either need 3 for resiliency and to have quorum if you lose a node, and ideally 5, which means if you lose a node, you're not very, very frightened while fixing it, because when you have 3, if you've lost 1, while you repair it, if you lose a second one, you're in a very big problem. So having 5 is usually better. However, for the other components, you can only have 2, you can have 4, you can have 5. So that's better. Another one is etcd is very intense on IOs and on the network. So that's important. And also, the other components are stateless, which means you can basically replace them very easily, update them, no problem. It's, of course, much more difficult with etcd because it stores data. So the first thing we did, and this is the design of our first control plane, is we moved etcd nodes outside of the masters. And so now we have these three masters, or n masters, when you have API servers, schedulers, and controllers. So that works a lot better. However, this is not perfect either. The first thing is, you can see on this graph that I highlighted one scheduler and one controller, because this component use leader redaction, and at any given time, you only have a single one running. So there's actually no point in having more than two schedulers or two controllers, because anyway, at any given moment, only one is going to be running. In addition, something that's important is when you start to run at scale, the controller is going to be pretty intense on the API server, and so the API server in the middle here, where the controller is running, is actually going to be loaded much more than the two other ones. And ideally, you want controller to establish connections to multiple API servers, so load is more balanced. And another thing is API servers, scheduler, and controllers have very different profiles. API servers are very intense in memory and network, while schedulers and controllers are much more intense in CPU. So it actually makes sense to separate them. And now we get to this design, which is the one, sorry, we've been running for a while now. So you have etcd nodes, API server that you can scale horizontally, and two schedulers and two controllers. And of course, you still have your kubelets and your customers, your client connecting to the load balancer. So this is nice. I mean, we have this very, very nice drawing with boxes and colors and arrows. But as you can imagine, once you've gone there to this like whiteboard design, you actually need to implement it. And the first thing that's important is all these arrows are actually critical data paths that you want to encrypt and that you want to secure with authentication. And this gets us to this second part here, which is how we're going to secure the control plane. So we're lucky because Kubernetes uses certificates a lot, and you can use certificates for everything. And even if you look at the hardware from KCI Tower, the tutorial, you're going to see that you're going to create certificates. And this is the configuration of the PKI used in this tutorial. Something that's important here is you can see this little number here. So if you do the math, this is exactly a year. And if you look at many stories of people that have been using Kubernetes, they're going to tell you, well, everything was working fine until about a year, where everything started to break. So yes, I mean, Kubernetes uses certificates everywhere. It's a very common source of incidents for people that have managed certificates. And so we decided from the get-go to rotate certificates daily. It's not that easy, though, because I mentioned certificates, and you're going to see that there are a lot of them. The first connection you need to encrypt and secure is the etcd communication. So the communication between etcd peers and from the API server to etcd. So in our case, what we do, we use Vault as a PKI. And so etcd peers are going to download certificates from Vault and are going to rotate them. And same for the API server. It's going to get a client certificate from Vault and connect to etcd. So this is the first part. But then you have all these components that need to connect to the API server. So you need a server certificate from the API server, but you also need client certificates for all the components connecting to the API server. In this example, controllers, schedulers, and of course, kubelets. Well, we're not done yet. If you use Kubernetes, you've heard about service accounts. So service accounts are basic users in the cluster that allows communication application from inside the cluster to have credentials on the cluster. And the way this works is when you create a service account, there's a specific controller that's going to create a token for the service account and is going to sign it. And you can see here that the controller is getting a private key to sign service account tokens, and the API server is getting the matching public key to verify them. Another thing is sometimes the API server needs to make outgoing calls, so call to additional services. If you want to do admission control or mutate your resources. So for this outgoing connection, you also need client certificates. And in this case, we have this additional PKI to get these certificates. And finally, and I promise you this is the end for this slide, you need to have users connect to your API servers, and you want your users to authenticate. In our case, we want to use single sign-on, and what we do is we use an OIDC provider. So what happens is a user would get an OIDC token, send it to the API server, which was then verified with the provider. So this is the way we've done it. You have many other ways to do it. A very quick explication on the reason we did it this way. We separate the PKI because they are very different in terms of rules. For instance, there's no reason for anything to get a certificate that is valid in the etcd world. Same for the API server. We only want certificate that connect to the API server, and it's isolated. Then you have API service, which is connection outgoing from the API server. And finally, you have the last blue box, which is a KB store when we have to store these matching public and private key certificates for service account tokens. So as I was saying before, our plan was to rotate all certificates very, very regularly. But of course, we made a few exceptions. And it wasn't such a good idea. So the first exception we made was to use something that's called TLS Bootstrap. So TLS Bootstrap is a way for kubelet to get certificates. So the way it works is an admin would create a Bootstrap token. In our case, we would just add it to Vault, and the controller would get the signing key I was mentioning before to sign the kubelet certificates. And then this is the TLS Bootstrap mechanics. So first, the kubelet would get the Bootstrap token I was mentioning before. It would authenticate to the API server using this token. The API server would verify this token and associate group to the user. Then the kubelet would create a certificate signing request, and the controller would verify it and sign it if it had the credential to get certificate signed. Finally, the kubelet could download the certificate, re-authenticate with it, and register the node and be part of the cluster. So that's a bit complicated, but that was very convenient for us because we didn't have to manage anything with the kubelet. However, one day, we realized that some kubelets were failing to start and to register, or that some of them were taking tens of minutes to start. There was nothing in logs, and so we looked at the API server audit logs, which are the logs of all the API calls made to the API server. And we noticed that all these nodes were stuck waiting for a certificate. So they had created the certificate signing request, but were not getting a certificate. It turned out we had a lot of certificate signing requests in flight. So you can see this graph here. It's the number of CSR in the cluster. And if it's not obvious, like lower is better. So when it goes down, it's when we fixed it. And so I'm pretty sure you can see the figures in the back. But at one point, we had more than 15,000 CSR in flight. And of course, you have this control that at every synchronized loop is going to try and sign all certificates and verify them, and it's taking longer and longer. So why did this happen? Well, it turned out the kubelet has two different ways to request certificate. The first one is during the bootstrap phase, when it authenticates with a token. And when it has a token and a certificate, when it's doing its renewal, it's actually authenticated using its own certificate. However, we had a mistake in our airbag policy where the bootstrap token was allowed to get certificate signed, but not the node, which means the node were creating certificate signing requests, but the controller was not signing them, and of course it breaks. So yeah, and the very bad thing about that is, of course, you notice it after a year. Well, we had a second exception, and you're going to see it didn't go very well either. So we had a very temporary solution, we thought, when we built our first admission controller. And all these mechanics were not ready yet, so we decided to use a self-signed certificate. So create a self-signed certificate, store it in Vault, have the admission controller start, pick the certificate and private key from Vault, and then the API server would connect to it and verify it. It worked fine, and of course it was temporary. And after a year, suddenly people were complaining that some calls and some resource creation were failing because this certificate had expired. So the key takeaway is, well, if you do Kubernetes and operate your clusters, think about certificate very early and rotate them often. It's hard, but well, when it's hard, do it often. And also it's very good because in the end it's gonna really help you. So I've mentioned how we get certificates and how we renew them by using Vault. But of course, sometimes you need to notify application that the certificates have changed. and some applications don't support being dynamically reloaded. And a very good example of that is the API server. So on the top graph here, you can see the restarts of the API server in a cluster. And as I was mentioning before, we have a large number of API servers, and we restart them daily to reload certificates. If you look at the second graph, you can see the etcd traffic. And you can see that that's exactly aligned with some API server restarts, we have a huge spike of traffic from etcd. And the reason is because when the API server restarted, all its caches are empty, and so it needs to download pretty much the whole cluster view in memory. And the last graph at the bottom is the performance of etcd, so it's the number of slow queries. And you can see that exactly at the same time, API server restarts, it generates a lot of traffic, and etcd becomes very slow. And another problem is we have a lot of applications connected to the API server. And in my example here, we have core DNS. So exactly the same type of graph as before. You have the API server restarts at the top. And you have the impact on the memory usage of the core DNS pods at the bottom. And as you can see here, when the API server restarts, there's a spike in memory usage from all the core DNS pods connected to the specific API server. And the reason is, well, the core DNS pods have an in-memory cache of everything they need. And when the connection is dropped and they reconnect, they need to replay the cache. And of course, it's consumed more memory on their side. Something that's important too, as you see on this graph, is the traffic to API server is not balanced very well. So you can see on the top graph that the traffic for all the API servers, so all the traffic going out of them, and you can see very different periods, which mean, and every one of them matches a restart of an API server. So you have the first one on the left, and second one, third one, and fourth one. And what's important here is you see that at no moment the traffic is balanced. So it's very different. You have one API server that's sending 15 megabytes of traffic per second, while another one is sending only 2. On the bottom graph, you have the exact same view in terms of number of connections to each API server. And you can see that we also have a huge difference. And the reason for this is all clients of API server are connecting using long-lived connections because they watch events from the API server, so they only get notified when something changes, which is nice. But of course, since these connections are long-lived, when you disconnect an API server, all these connections are going to be rebalanced on others, and you have these changes, like these huge changes happening all the time. And of course, you can imagine from this graph that if you look at the right-hand side, when the API server on the top is restarted, the impact on the cluster is much worse than the one on the bottom because it has this huge number of connections. So a quick takeaway on this part is restarting components is not transparent. I talked about API server here, but it's not limited to API servers. We've had some issues with Kubernetes too. And it would be really great if component could transparently reload the certificates. Also, if client could be a little clever and instead of reconnect immediately when they lose the connection, wait a random number of seconds. So reconnections are spread over time. And it would be very great if there was a way to rebalance connections over time. A good idea would probably be to just kill connection randomly after a certain number of hours. So when you reconnect to the load balancer, you get something that's more balanced. So now we've got this nice secure control plane. And the second thing I want to talk about today is how to do efficient networking, which is something also you won't ever see in a Kubernetes 101 because it's a bit complicated. So we have specific challenges in terms of network because we have huge throughputs and our applications are very heavy on the network. So we want it to be efficient. And also we have pretty large clusters. I was mentioning before between 1,000 and 2,000 nodes for most of them. And finally, we have multiple clusters and we want to manage traffic between clusters. And since we haven't finished migrating, we also need to handle traffic between VMs, so not part of Kubernetes, and clusters. So the first thing we need to solve is how the solution we're going to choose to get IPs to pod and to route all these pod IPs in the cluster. So if you follow the tutorial from the hard way, at one point you're going to see this command there, and it's basically creating routes in GCP for all the nodes. So you have two parameters. One is the pod CIDR, so the CIDR for the pods on a given node, and the other one is the IP of this node. And basically, this command is creating a static route in GCP to say, for this pod CIDR, send traffic to this instance. So for small clusters, this is actually a good idea because it's very simple. It just works. You have an example here. I'm just saying, OK, on node 2, I have pod CIDR 10.0.2.0. And I say, OK, for all traffic to this CIDR, just send it to the node 2 IP, which is 192.168.0.2. That works fine. However, you can imagine that it's very hard to scale. If you have hundreds, thousands of nodes, it won't work. The first reason is if you have limit on the cloud provider side. To give you an idea, on AWS, you can't have more than 50 routes in a VPC. So as long as you have less than 50 nodes, you're good. If you go above it, you need another solution. So for mid-sized clusters, a typical solution is to use overlays. So in that case, what an overlay solution is going to do, it's going to tunnel traffic between hosts. Okay? So in this example, I used VXLAN, but some solutions use IP/IP. I'm pretty sure we could use GRE. And the idea is you completely ignore the underlying network, and you just tunnel pod-to-pod traffic using this tunneling solution. The most well-known solutions to do this are Calico or Flannel. So this works fine, but it comes with two little problems. The first one is performance overhead, because, well, you need to tunnel traffic, so you have additional headers, you have additional CPU processing. And also, as you get bigger, you also have control plane issues, because you actually need to distribute this information across your network, and it starts to be complicated. So if you get to large clusters and you have a lot of traffic, I'd recommend you use native pod routing. And by this, I mean give IPs to pod that are routable on your network and that are native in your network, so you don't have any overhead. It's much better in terms of performance. You have no overlay. The control plane is usually simpler. And also, it solves another problem that was very interesting for us. Since all pod IPs are routable, you could actually access them directly from outside the cluster, which can be convenient at times. So in practice, how do you do that? If you're on premise, well, you're in luck. You can do this with BGP. You just have to have all your hosts participate in the network topology of your network and just be BGP peers and announce their routes to the network, in which case it's just going to work. If you're on the cloud, it's starting to get a little more tricky. On GCP, there's actually a feature called IP aliases, which allows you to alias CIDR ranges to interfaces, and then everything is routed magically by the VPC, so that's very convenient. And this comes from like the GCP network guys sitting very close to the people developing Kubernetes, and they're working together. On AWS, it's a bit more complicated. So the way it usually works, if you want to do native routing, is you would allocate additional ENIs, so additional interfaces to your hosts, add additional IPs to this interface, and then map this IP to pods. So you use IPs from the VPCs, and you associate them to pods instead of instances. And I put them like several plugins that can help you with that. And just to give you an idea of how this works for all these solutions, when you have your normal kubelet that calls your container runtimes, that calls CNI, this CNI binary is going to ask for IP to a local agent, and this agent is going to talk to the AWS API and manage additional interface and additional IPs, and this IP are then going to be associated with pods. So in my example here, you can see that IP1 is an additional IP on interface 1, and it's been allocated to pod 1. That works fine. There's only one additional trick that you need, is you need traffic to be routed on the proper interface, of course, because since IP1 is associated to interface 1, you want traffic from IP1 to go through this interface and not the main one, so you also need to manipulate routing on the host to avoid traffic being dropped by AWS. A quick takeaway on this topic, I really think native pod routing is going to be the future for all clusters because this is what scales best. It's a bit more complex to debug. Solutions are a bit younger, but it's much more efficient in terms of data paths and opens a lot of things you can do with them. The topic is still dynamic. For instance, Cilium, which I mentioned before, which is a CNI solution providing other things, introduced ENI support very recently. I think it was in 1.6, so a month or 2 months ago. And one thing that I also wanted to mention is we've been using the Leaf plugin heavily in production. And we're now starting to use the Cilium one, and we've had a very good relationship with both these teams, and it was very easy for us to work with them and do PRs and extend their solution. So now we have networking set up, and we can allocate IPs to our pods. The next thing we want to do is to be able to access Kubernetes services. Okay, so Kubernetes services are virtual IPs that are load balanced on the client side, so on the host. So you connect to this virtual IP, and magically, these IPs are going to be routed to pods. You have two main ways to do that, and the first one is to use, so the tool responsible for this is called kubeproxy, and the first way to do this is to use IP tables, which is the normal way to do that. So just to give you an idea, on the mid-sized clusters, so very, very far from the ones we're running today, a normal setup would have 50,000 IP table rules. And a lot of people have had issues because once your number of nodes and services is getting pretty big, well, we're talking about megabytes or dozens of megabytes of IP table rules. And everything is generated every 5 seconds and loaded in the kernel by replacing all the former rules. And what happens when your cluster gets too big is you hit a timeout because it takes more than 5 seconds to reload all these rules and things break. Not ideal. There's a nice alternative that's been around in kubeproxy for some time now, which is IPVS. So when I saw this option, I was like, well, it makes a lot more sense to load balance traffic using IPVS than IP tables. It seems like much more natural to do it this way. And the way it works is, so service IPs are mapped to virtual servers in IPVS, and pods are mapped to real servers. And so kubeproxy is going to watch the endpoint of the services on the API server, and it's going to create, update virtual servers and real servers. So this is how it looks. And when you establish a connection, so if app A wants to talk to service S, and there's no connection established, IPVS is going to find a backend and associate this connection with the backend by creating an entry in the IPVS connection tracking table and say, okay, if I see traffic from A to S, then I translate it to A to X. Okay, so traffic is now going to be sent to pod X. This looks fine so far. Now, what happens when a pod is deleted? So when a pod is deleted, the API server is going to remove it from the endpoint, and kubeproxy is going to remove it from the real server, which makes complete sense. However, for those of you familiar with IPVS, when you remove a server from the real server list, all traffic to this real server is just going to be dropped by the kernel. So this is the red cross in the middle of the slide. Usually, it's not that big of a problem because when your pod exits, it's going to send a FIN, and it's going to trigger garbage collection in the contract, and the connection is going to be terminated, so you're good. Except sometimes, your pod is not going to send a FIN. The usual reason is your host is going to crash badly because there was a kernel panic or because it's the cloud, you know? And what happened in that case is traffic is completely black-holed until the application notices that something is going wrong. And the way it's going to notice that is it's going to send traffic, and it's going to notice that it's not getting ACK back, okay? And the way it works, it's going to retry 1 time, 2 times, usually 15 times. And since this is exponential, it's going to take 15 minutes for the application to find out that there's an issue. And the first time we had this issue, I mean, it was a pretty bad one. So to mitigate this, there's actually a setting in IPVS, and you can say, well, if I see traffic to an entry in the contract with no real server, instead of black holing things, what you can do is just garbage collect immediately and send a reset to the application so you know immediately. So that's a lot better than what I was showing before. However, this isn't very graceful. What you usually want to do is when you terminate a pod, you want the pod to have a graceful termination period, usually a minute or so, where it can just finish all the connections and send all the traffic it needs to send and properly shut down. Of course, once you put this pod in terminating state, you remove it from your server, there's no point in doing graceful termination because the connection is going to be dropped immediately. And of course, people working in kubeproxy were trying to address this, and the way to do that was a bit natural in terms of IPVS. So what you do is when you notice that an endpoint has been removed, instead of removing the IPVS real server, you set the weight to 0, which means established connections are still going to work, but you won't establish any new connection to this server. And what's going to happen is after there's no active connection to this real server at all, kubeproxy is going to garbage collect and remove the real server, and then we're good. Well, when you delete a pod, sorry, so this is the garbage collection part. So when there's no thing anymore, kubeproxy is doing garbage collection, remove the entry in the contract because there's no active connection, and we're good. However, we get back to the situation I was describing before, which is what happens if there's no FinSend. In that case, the connection is never going to be marked as terminated, and so you rely on detecting that the connection is stale, which means it's usually going to take 15 minutes. And today, the only way to address this is actually to lower the number of retries you're going to do. So instead of doing it 15 times, you only do it, for instance, 8 times, and it's going to be much faster. Not ideal, but a lot better. So a key takeaway is, well, IPVS has worked pretty well for us, and we run it at a large scale. It's in a pretty good state now. To be honest, it took some time to get there, and it was a lot harder than we expected. And somehow, along the way, I became a reviewer and approver of IPVS because I was so involved into making it work. The last topic I want to talk about is ingresses. So how to get data inside your clusters. So just to give you an idea, imagine you have this type of setup where you have VMs and different clusters. And in this example here, imagine application A on a VM that wants to talk to application B in cluster 2 or application C in cluster 1. You want to solve this. And of course, if you're application B in cluster 2, you also want to be able to reach application C in cluster 1. So the usual way to do this with Kubernetes is to use a load balancer service. So for those of you that are not familiar with Kubernetes, when you have a service, you can extend them to be load balancer services, in which case Kubernetes is going to do two things. It's going to allocate a node port that's going to be the same across the whole cluster for this service, and then it's going to create a load balancer, a cloud load balancer on AWS or GCP or Azure, and this load balancer is going to send traffic to this node port. Okay? And once traffic gets to an instance, any instance, it's going to be load balanced by kubeproxy to the pod that are backing the service. So this looks fine, but imagine if you have thousands of nodes. It means you attach thousands of nodes as backends to the load balancer. And actually, even a cloud load balancer have limits. And for instance, we've had incidents because people were using load balancer service on a cluster with more than 1,000 nodes, and since we're not working anymore. Another problem is it's not very efficient in terms of data paths. So imagine you have a web application sending traffic to your cluster, like heavy traffic. Traffic is going to be dispatched across all the nodes, and then it's going to go back to the proper pods. But sometimes it's going to go on nodes where you run critical workloads, such as Kafka, for instance. And you wouldn't want a Kafka node that's very loaded to also have to manage web traffic for another application. There's a trick you could use. So usually when I mention this to Kubernetes people, they say, well, use external traffic policy local. So external traffic policy local is actually a hack where you tell kubeproxy to fail health checks on nodes where there's no pod running. So what's going to happen is that you're still going to have to register all your nodes as backend to the load balancer, but you're going to trick the load balancer into into using only the nodes where the pods are running. So that works better, but there are two things. The first one is, well, you still have the limit of the number of backends behind your load balancer. And then at one point, we get to a size where health checks were actually DDoSing our cluster because we were sending so many health checks to so many nodes. So not ideal either. Of course, when you talk about these to people, they're going to say, well, use a more clever Ingress controller, such as Nginx, HAProxy, or Trafic. So when they say that, they mean use an Ingress, which is an L7 proxy in my slide. And this layer 7 proxy is clever, and it's going to route traffic directly to pods. However, as you can see on this very simple schema, you still need to get traffic to your L7 proxy, and so all the problems I was mentioning before are still exactly there. And also now, somehow, you also have to manage and scale your load balancer, whereas before, everything was managed by the cloud provider. So yeah, this is a summary of the challenges. It's hard, and there's no ideal solution. So what we wanted to do is to do native routing. So just to get back to what I was saying at the beginning, is our pods have routable IP, which means we can actually route traffic from load balancers directly to pods. And there's different load balancers and different controllers that support this. And for instance, in this example here, on AWS, you can use a controller that's called the ALB Ingress controller that's going to drive an Ingress by using an ALB. And this ALB, so this application load balancer, is going to use IP as backend, and you're only going to register the IP of the pods. And so it's much more efficient in terms of traffic. So when you see this, you're like, OK, we have a perfect solution. Well, not completely. The first thing is this solution only works for HTTP traffic. There's no support for TCP or UDP, so if you need them, it won't work. And also, the worst part is registration delay. The very good thing about Kubernetes is it's very fast to update and roll out pods. However, here, we have to interact also with cloud provider and do an API call to register endpoints. And of course, this is much slower. So you can end up in a situation when you replace all the pods in your deployment, but the load balancer is not aware of it yet, which means you don't get traffic to your pods anymore. Not great. So there are mitigations. So the one that was recommended by Google for load balancer at Google is to use a feature called min ready seconds. So usually people don't know about this. It's basically a sleep. You say, OK, wait for X second before a pod gets ready. So people would recommend setting it to 60 seconds, for instance. And so if your API calls take more than 60 seconds, well, it's not going to work. The better solution would be to use pod readiness gates. So pod readiness gates are a feature where you can modify the way readiness works for a pod. So it's usually only using a health check, so a readiness check. But what you can say is, say, this pod is part of something that's external, and you need this external thing to clear the gate before the pod is ready. So in my example, what you can do is say, OK, the controller is only going to clear the gate once the IP has been registered in the load balancer. So the pod won't be ready until it's registered with the load balancer. So that's promising, but it's still something that needs to be done. So to be completely transparent, today this is the solution we use. So it's a pretty ugly workaround where we run layer 7 proxies in host network on dedicated nodes with stains. And we have load balancers that we manage manually, and we attach to these nodes. So we have stable IPs, and we have a way to actually get traffic into the cluster efficiently. So this is not great, but I mean, at least it works. So yeah, ingresses in Kubernetes are still pretty tricky, and there's still a lot of work to do to make them production ready at scale with a lot of traffic. And this gets me to my conclusion. There were a lot of other topics I would have liked to discuss with you today. One of them is DNS, because we've had so many interesting DNS issues. Another one is how you manage stateful applications. We do this a lot, and it's been tricky. The one that I like the best is how with daemon set, you're probably going to end up DDoSing pretty much anything once you start having thousands of nodes. because when you deploy something 1,000 times, the probability that you're going to break something is very heavy. And also some life cycle issues and how to deploy applications to your clusters. If you want horror stories, if you like them, I do. We've done several talks on this topic. And also there's this very nice repo at the bottom with a lot of horror and failure stories of Kubernetes. So the key lesson, well, managing Kubernetes yourself is hard. If you can, don't do it. Just use a managed solution. Networking is really not easy. And don't forget that the main challenge is not technical. You're going to have to build a team to do it. And also, there's going to be a lot of transformation in your organization. You're going to need to train people, and you're going to transform practices. And this is probably going to be even harder than actually doing the technical parts. Thanks a lot. I'm a bit over time, but I'm going to be around if you have questions. And also, do not hesitate to reach me on Twitter if you have any questions. And the last thing is, if you enjoy this kind of horror stories, we're hiring, and we're looking to find people that love these kind of things. Thank you.